Welcome back to another video in the Calculus 1 playlist, and in this video we're going to use derivatives to look at minimums and maximum of functions. And to have a little bit of motivation for why we're doing this, we need to kind of familiarize ourselves with the concept of optimization problems. And optimization problems are kind of self-explanatory. It is a problem where you work to optimize something. But nevertheless, all of these optimization kind of problems, they probably use some kind of derivative of some function. And it turns out that derivatives can help find minimums and maximums of functions. So if we just have some function here, and that is a function of x, there's a little bit of terminology that we just want to define. So we can have an absolute max if at some point in that function, the value for f of that point is greater or equal to all of the other values on that interval of x. So you can think of that as this point right here. And we can obviously see that it's a larger value than every other point. And we can also have an absolute minimum. So similar to the max, except now we have some point that's lower than all of the other points on that interval. So right here, this would be our absolute minimum. And then we can have our local maximum and local minimum. And we represent that as some maximum or minimum value near some point. But this local maximum is not greater than the absolute maximum. So we can investigate something called Rolle's theorem. And in this theorem, we consider f of x being continuous on some interval. So we could have some endpoints a and b, and f of x is continuous. But we also need f of x to be differentiable, except now we don't have to include those endpoints a and b, but we still have to be within that domain. And Rolle's theorem specifies that the endpoints are equal, so we could say that f of a is equal to f of b. And if all of these conditions are met, then there exists some point, call it x equal to c, some critical point, where the derivative of that function is equal to 0. And just drawn out here, we have 3 examples. So if we look at this first example, notice our endpoints, we violate this condition right here. But in this middle example, we're okay with this. It seems to be continuous and differentiable. And we know that the derivative being equal to 0 would represent when the slope would be equal to 0. So I think we can see where that would be on the middle graph. And then on the right here, we just have a function. And I tried to make it a straight line. So you could say that f of x is equal to a constant. So we know that the endpoints are definitely going to be the same value. And everywhere on this function, the derivative is actually equal to 0. But this isn't the only theorem that we have to consider, and we can actually generalize this. So again, if we have that continuous function on an interval and it's differentiable, then we can say that that function has a point where the slope is equal to the average slope over that entire interval, or we can express that like an equation, and that is what we're going to define as our mean value theorem. But moving forward, we have a lot of words so far, not a lot of actual math going on, but we're probably interested in how we get these minimum and maximum values with derivatives. And if that derivative is equal to 0, we know that slope is flat, and we know that we can correspond this flatness to some minimum or maximum. But if we actually want to think about getting this minimum or maximum value, well, maybe your first instinct is find where that derivative is equal to 0. That'll give us the location in the original function f. And what we could do, we could plug in these values into f of x. Let's say we had some critical point, x1, and we could look at the limit as q goes to 0 of f of x1 plus or minus q. And we would compare that to what the value of that critical point gave us. You can kind of think of this if you had some graph. We found this critical point, x1. What this limit here is going to do, it's going to show us the nature around x1, but the derivatives that we're looking at, those can actually be quite useful, because recall what that derivative is again, and it's going to represent the slope. So if that derivative is greater than 0, it means that we were increasing, and if it's less than 0, we're decreasing. And putting even more words onto the whiteboard, if we had that critical point x1, where that derivative was equal to 0, if we had the derivative at x1, so we look at it before x1 and after x1, if that changes from positive to negative, then we can say that we had a local max. But if it changed negative to positive, we had a local minimum. And I think, yep, this finally gets us into our example. So we are going to consider the function y equals x to the fourth minus 4x cubed. But we're going to consider when that derivative is equal to 0. So that's going to occur at x equals 0 and x equals 3. So what we can do, we can take that function for the derivative, and we know that we have critical points at x equals 0 and x equals 3. So if we plug those into our original function, we can find what those values are equal to. So we have a 0, 0, and then a 3 minus 27 right here. And because we have two critical points and we need to investigate what's happening at those critical points, we're going to investigate three different areas. So the first one's going to be from minus infinity to 0, then we have 0 to 3, and then we have 3 to infinity. And we don't actually have to plug in any numbers here, because we just want to know if it's less or greater than 0. So if we look at this first interval that we're looking at, we know that we will be plugging in some negative number. And if we plug in a negative number to this equation right here, we have a negative number times a negative number. And in parentheses, we're going to have another negative number. We would get a negative result. So we know that the derivative is less than 0. So we could say that f is decreasing. So if we look at the notes from above, we know that we have some transition point at 3 where we go from decreasing now to increasing. And that would correspond to a local min. So we would have decreasing from minus infinity to 0, decreasing from 0 to 3. And then we get that local min right here at 3, and then we're increasing again. So we have something that looks like this. We can add arrows to it because it's a continuous function. And this is a good starting point, but we don't really have much resolution at those critical points. We don't really know what the shape of the function looks like. And that's when we need to start looking into the second derivative and when that's equal to 0. And this is going to refer to what we're going to define as the concavity. So we can have an upward or a downward concavity. And this is going to get us into inflection points. So our rules look like this. If that second derivative is greater than 0 on some interval, we're concave up. Less than 0, then we're concave down. And we can come back to the original function, but now we're going to be looking at that second derivative that we found. And from that second derivative, we have a 0 when x is equal to 0, and we have a 0 when x is equal to 2. So if we look at that second derivative, and we look at that first interval, so we get some negative number, so we get negative number times some negative number, that'll be a positive. So that second derivative is greater than 0, so we have concave up. And if all of this is confusing, there's a very quick way to summarize all of this. And we're going to consider this function here. So we've broken it up into 4 zones to kind of show what the nature of the function would look like, its derivative, and then its second derivative. And this brings us back to looking at our first and second derivatives. So now we're going to do some interval matching. So if we look from minus infinity to 0 for both the first and second derivatives, you see that y prime is less than 0, and y double prime, or the second derivative, is greater than 0. You could correspond that to zone 1 right here, so we know that our function would look like this. But now we can get into the middle part, so consider the interval 0 to 3. We know that y prime is going to be less than 0. And if we look at the interval or the second derivative, we only have it defined from 0 to 2. But we know that y double prime is going to be less than 0. And we're almost done now. We just need to see what's going on between 2 and 3. So we know if x is equal to 2.5, we actually fall in this interval for the first derivative. So we know that y prime is less than 0. But if we look at x equals 2.5 for the second derivative, we actually fall into this interval, where we know that the second derivative is greater than 0. So we have less than and greater than for the derivatives. So we know that that actually puts us again into zone 1. So we're in here 2 times. So we know that from 2 to 3 on our function f of x, we're going to have some kind of function that looks like this. If you learned anything new or useful, please like, comment, share, subscribe. We'll see you in the next video where we look at a new topic. And thank you for watching.